is very much core to numerical algebra, right? So tensors extend the functionality of matrices to higher dimensions. They have appeared in Feynman's diagrams, they've appeared in psychometrics. So there's a rich history of tensors, but how are they now applicable for modern machine learning at scale? And I'll show you some examples here on how, by exploiting multiple dimensionalities, how by exploiting higher order relationships in the data, you can get much better performance, and at the same time design them to be computationally efficient and parallelize them to run on these distributed systems. So I'll try to put all these three threads together. So how many here work in the AI space or have, yeah, so that's a good mix. So I'll try to keep the talk broad. I also want it to be interactive, so anytime you have a question, comment, feel free to interrupt. So indeed, deep learning has been in the news almost every day now. There's been a tremendous improvement in performance in almost every domain. Right? So it started with the image understanding task where you're given an image, can you identify what are the objects in this image? I mean, for humans this is trivial, right? But it's very, very hard for computer vision algorithms to achieve this. And the first time a significant boost in performance happened with the ImageNet contest was with a deep learning system. So ImageNet contest is a yearly contest that has been popular in the computer vision field. It has more than 1 million images. And this was the first large-scale data set. So before that, the earlier data sets were an order of magnitude smaller. And so this boost in data, this availability of large-scale data, showed the strength of deep learning system. Right? So, I mean, if there is one thing to take away from the talk, right, it's like without data and computation, there is no machine learning. Right? So algorithms are, of course, needed, but what we run today in practice are very simple algorithms. And what we really need for the systems is extremely large-scale data. And to be able to process this large-scale data at within a reasonable time, you need large-scale computation. And that's why cloud infrastructure is ideally suited because of its elasticity. You can easily scale it up. You can easily have tasks done in large scale. And so that's the history, like deep learning around 2011, 2012, started taking off, and with the boost with the ImageNet contest, there was a lot of excitement and interest to see how it applies to other domains. And the same thing happened with speech recognition compared to the classical approaches. There was a big boost and companies started using it for speech recognition. Natural language processing is understanding text. Like again, given just the text document and can you parse what it is saying, right? Can you categorize documents? Can you classify sentiments? Whether this review was a positive or a negative, can you do this automatically? Again, these are tasks that are extremely complex, and text is hard because it's got discrete data. The words are discrete, characters are discrete, whereas image is continuous. And it has been more challenging for deep learning systems to work on text, but at the same time, there has been continuous improvement. I mean, to me, the last aspect of autonomous driving is the most challenging and at the same time most exciting, right? So this is where deep learning system is put in a loop. It's continuously learning, but it's also affecting the decision making, and there are some very strong safety considerations, right? And that's why it's very challenging to do learning on the fly. Most of these algorithms are done offline, and then you put it on the vehicle. So it's still an open problem on how much learning can you do online. Can you, process data and learn new aspects? So that's still a very open question. And the CAST initiative at Caltech, that's one of the things we want to resolve. Like, can we have robots that can walk autonomously? In fact, if you go to the CAST website, one of the moonshots for our decade plan is to have a Cassie, which is a bipedal robot, walk up the coastal trail autonomously, surrounded by drones. I know it sounds ambitious, but you know, we are very excited to see if we can make that moonshot. And so yeah, so as you can see, like AI spans a lot of domains, and deep learning has shown improvement whenever we are able to gather large amounts of data, right? And in these applications, you can scrape off the web, you can crawl the web, and assemble this data pretty easily, and that's where we've seen the most benefit. In other areas like biological systems, right now there has been increased data collection, there has been improvements in technology that has enabled us to do that, and that's where we'll also start seeing benefits of deep learning in those domains as well. So the canonical deep system is these multiple layers of processing, right? So in this example of image classification, you input an image, you want to output what are the objects in this image, right? So along with their confidences. I mean, you know, if the system is not completely confident, it will show a lower value. In this example, like 85% confidence that there's a dog in this image, right? And there could be also some non-zero values for other categories like cat that has some shared features with a dog, but at the same time there is enough to distinguish, so it has a lower confidence. And so the idea is because you're processing these in so many layers, you can progressively filter the nuisances or the irrelevant information for saying what's a dog, and only take what's relevant to the final layer, right? That's what these multiple layers of processing gives you, which wouldn't be possible if you just had a shallow network. Even if you had a very wide but a shallow network, you wouldn't have these layers of processing. And so and this is one of the innovations that has been done now compared to what people were trying with neural networks, say in the 80s or 90s, right? So there mostly it was shallow networks. It was not this large-scale models, and that's also because we didn't have the computer technology to enable that. We didn't have the GPU power that we have today. And so to me, like the AI winter that was caused in the 80s, where neural networks did not work out, was primarily caused because of lack of data and computation. And that's the primary thing that has changed, right? I mean, we've seen a few algorithmic developments, but we are still a long way to go in order to think of the most optimal algorithms. And so that's the idea. You have these multiple layers of processing. And with images, again, you can further specialize what these processing units should be. Because in the image, you want to detect a dog no matter where it is placed in the image, right? The convolution operation is translation invariant. So it's able to detect the same features no matter where the dog is in the image. And that's the reason why they've been used in these image processing networks. And so there are convolutional layers, and then towards the end, towards the last part of the networks are so-called fully connected layers. They are nothing but a series of linear algebra operations with some nonlinearities. Again, think of them as layers of filtering that enables us to come up with very accurate answers of what's in an image. So that's the high-level idea of what these deep learning systems are doing. I mean, indeed, if you want to go into the details, there is so much we still don't understand, right? Because, think of these networks have grown to be so large and so complex, it's very hard to interpret what each processing unit is doing, what each neuron is doing. Like, we can get macro scale behavior, but micro scale is not something we can do very well. And that's true with any complex system, right? So even with physical systems, we can do experiments, we can have hypotheses, we can test them. So to me, even with these artificial neural network systems, we've reached a point where we need to think of them as complex systems that we may not be able to interpret every minute unit in it, but we can think of the overall behavior and study that. And to give you an example of one of the state-of-the-art networks, the Inception V3 network, it was one of the ImageNet winners, I think, over the past 2 years. It has more than 100 layers, right? So without even worrying about what each specific unit is doing, you can see that this would be extremely complex to program if you had to do it from scratch, right? And we machine learning scientists are not the best programmers, right? That's not our expertise. And so to me, what has also driven a lot of development in this field has been the availability of open source packages. And so machine learning has had a lot of development out in the open. You know, all the companies have been publishing papers, have been open sourcing software. And that, to me, is different from what other revolutions look like, in other fields how it looked like. Right there, it's very closed off, whereas machine learning is very open. And to me, I think this is almost a necessity, because if you want to have impact across different domains, the only way is to have open sourced and be usable by everybody on the planet. And so one of our missions at Amazon AI within AWS is to help democratize AI, like how we can provide cloud infrastructure for research, for education, for nonprofits, as well as for startups. So we have generous credit programs. If that's something that you're interested in, talk to me. And so one aspect of democratization is how can we enable